So I think yesterday we were finishing off with polytropes, you'll be pleased to know, and now we're moving on to looking at the next two stellar structure equations. So we have the luminosity equation, and the next equation, the final equation that we really need to include in our setup, is the temperature equation, and this is for the temperature gradient in a star. So you looked at this already in tutorial, so I just wanted to flash this up quickly. This shows that in general we have fairly small gradients in terms of the energy density, nu, and also the change in temperature. So because we have small gradients, maybe we can turn down the lights. We can use the diffusion approximation in order to treat our temperature gradients, and this is what we're going to do. So the diffusion approximation, so let's say you have a diffusive flux of particles per area per time between two regions of different particle density. So this is very general at this stage. So D is our diffusion coefficient, which is 1/3 times the velocity times some length scale, which is the mean free path of particles in our regions. So we can apply this diffusion approximation or this diffusion equation to our radiative flux. And so we can easily do that by saying for photons, let's call our photon flux J. We're going to call our energy density N. And then here, these terms in the diffusion coefficient, they will come from what we have for photons. For V, that'll be the speed of light, and this will be the typical length scale of a photon in a given region. So we can easily rewrite this in terms of the radiative flux or the radiative gradient in a particular region of a star. So let's do that. So I'm just rewriting that out. So we have the particle, so our J, our flux density is going to be for photon flux. Then we have our energy density, speed of light, our length scale of photons. And so then we can rewrite this as minus D, this is our gradient here, and then we're just writing this out. So 1/3 speed of light times our length scale times the gradient of our energy density. Now, we're going to restrict ourselves to one dimension in space. Let's assume our stars are spherically symmetric. They're not rotating, they don't have magnetic fields. We're talking about idealised perfect stars in some sense. But this is the easiest treatment. There are, of course, if we wanted to model stars properly in 3 dimensions, we can't make this approximation. But even today, with our fast supercomputers, it's still very hard to do that. So we still generally restrict ourselves to one dimension, and that will be the radial dimension. So now, U is AT to the 4th. So we learnt this when we looked at thermodynamics. So we can differentiate this just in the radial direction, which is what we've done up here. So this is just the TdR. So we have 4AT to the 3rd to TdR in the radial direction. So we're starting to build up an approximation. So we're starting to build up an equation for our temperature gradient. So we already see we have a TdR in there now, where our flux is just again in the radial direction. Okay. Now let's look at L or L gamma in a bit more detail. So this is just that same equation. I've just rewritten that up on the board there. Now, our typical length scale for photons is related to the density of a region. Okay? If the density is smaller, so for example in the outer layers of a star, photons can travel further. Likewise, in the inner regions, where it's more dense, photons can't travel as far. So we expect that this length scale is inversely proportional to the density. Okay? So we can write then L gamma, I think that's gamma, is proportional to 1 on rho. And let's say that there is a constant of proportionality, and let's call that kappa, because we always tend to introduce another Greek letter. But kappa will be an important coefficient that we need to learn about. So we're going to say our length scale for photons is 1 over the density of the region divided by kappa r. And this term here, kappa r, this r means radiative. So this is the radiative opacity of a region. So this really tells us, so this opacity is how much how much the material is absorbing or emitting photons. So it's sometimes called an absorber coefficient, and it is a really important quantity in stellar physics. Now this kappa R is an interesting quantity, and we will discuss that more when so we're almost finished with this lecture, then we're going to move on to discussing about opacity, and then so there's a whole fairly qualitative, you'll be pleased to know, lecture on this, because it's really quite important. Okay. So kappa R is an interesting quantity because it depends not just on the temperature, the density, but also on the composition and the material, as well as the photon wavelength. Because, for example, if you have high energy photons, they might be more likely to be absorbed by different conditions than longer wavelength photons. So when we treat this quantity in a real stellar model, for example, not a real star, in a real stellar model, we have to have kappa R as we generally have tables of this quantity as a function of all of these variables: temperature, density, and composition. Okay, so now so our flux now equals 4 AC over 3 t to the power third kappa R divided by rho. This is our L gamma times the TDR. Now our flux F is the luminosity divided by the surface area of a sphere at some distance r from your source. So we can finally obtain for the temperature gradient, so inserting F on the left-hand side here, rearranging for the TDR, we get this expression for the temperature gradient. And this is what we use in radiative regions of stars. So where the energy is carried by radiation and not some other type of radiative transport mechanism. Of course, I did ask you about what other sorts of mechanisms can transport energy, and we have, for example, radiation can transport energy, conduction, and there's also convection. So we have electron convection, we'll get to that later. But first of all, what about conduction? It's not so important for stars, but there are some phases of stellar evolution where we have to consider conduction, the transport of energy by conduction. So here, and this is especially applicable to really dense stellar regions. And generally, for example, the interiors of white dwarfs might be one region where conduction is important. So can we include conduction? We can. It's actually very easy. So generally like we have a kappa R for radiation, we can have a kappa C for conduction. So what we can do when we add in conduction, so this is what we have for radiation. So here we've just defined this term for radiation. So all of those terms here are for radiation. So when we have conduction, we can define the same term for conduction where we have a kappa C, which is our conductive opacities now, as opposed to our radiative opacities. And how do we do this in reality? Well, we would generally find tables of these things, or there are fitting formulae, or there are people who've looked into this in detail, and me as a stellar modeler, I would take their results and I would take their tables into my stellar evolution code, and these might be functions of temperature, density, composition, all sorts of things. And then I would look them up for the region of the star that I'm interested in. So we treat conduction basically in the same way as we treat radiation, using the diffusion approximation. We can't treat convection that way. Well, you sort of can and can't. You're not meant to, because it really is an advective process, because you're moving material around in a star. Okay. So conduction, so adding conduction, I'm not sure if this really helps. All this slide is really saying is that we can basically add on. So we have our kappa R for radiation, our kappa R, our kappa C for conduction. In fact, what we've just done is defined these whole terms for radiation, this whole term for conduction. And then when we solve the equation for temperature, we will just add on those terms. So this is that whole term for conduction, that whole term for radiation, times the temperature gradient. And so it would be an additive process. We would just be adding the contribution from conduction and the contribution from radiation into when we solve the equation for the temperature gradient. Okay. Struggling a bit today with just being able to talk. Okay, so this really ends this lecture. So we have looked at polytropes in some detail. We've also then now defined two other equations. So this is luminosity equation written as dLdr, so not dLdm, which is how we wrote it also yesterday. So it's really just the surface area squared times rho times some energy generation. And then we have our radiative conductive temperature gradient, which is dependent on some quantity, kappa, which will come from both conduction or radiation. In most cases, like a star like our sun, the conductive opacity is very small, negligible. So really it's just the radiative contribution. Okay, so now we're going to look at opacities in a bit more detail. Okay, and I haven't put lecture 7 up yet. I just forgot because I've been running around and stuck in traffic and all sorts of things this morning, so I apologise, but I will post it up next. Okay, so this lecture's, it's a combination of looking at radiation opacity and energy transport in a bit more detail. Okay, so let's look at this opacity kappa in a bit more detail. So the opacity of material is its ability to block radiation and absorb heat. This is what that quantity represents. It's expressed as an absorption cross-section per unit mass. So it has the units, centimetres squared, so this is a cross-section component per unit mass, per gram, if we're looking at in CGS units. So if we have perfectly transparent material, that would have an opacity of 0. If we have, for example, if you've seen bushfire smoke, this is something many Australians have seen. This is an example of material that has quite a high opacity because it's absorbing and transmitting quite a lot of the radiation that comes from the sun. Especially if you see, like at sunset, if you've seen a very smoggy or smoky experience, this is where you have something that's got a high opacity. Okay, so what are the sources of opacity that we find commonly in stars? There are 4 main types of opacity that we need to worry about. And generally though, when I take the tables of opacity, all of these would be included as one contribution, as a function of temperature and density. But we need to know what they are. So there are 4 main sources, and these are bound absorption, atomic transitions. We also have bound-free, and I'll look at these in a bit more detail. Free absorption. So some of you, who've heard of some of these things before? And Bremsstrahlung. Who've heard of some of these types of opacities? Okay. So the first 3 are known as true absorption processes because they involve the disappearance of a photon. Whereas the second is a scattering process. So the photon scatters off various things. Okay. So when we include the opacity with that kappa R term, it has to include the contribution from each of those different types of processes at a given temperature and density. Clearly, in some regions of the star, you're more likely to be, the opacity will be driven by one of these processes more than another. For example, in hot regions of a star, you can imagine that scattering processes are going to be more important, perhaps. Whereas in the outer regions, where it's maybe cooler, you can imagine, for example, that bound absorptions might be more important. Okay, so what do I mean by all this? Let's look at a typical energy diagram for an atom. So this is an atom. I'm not specifying the atom that it is. So this is the ground state of our atom, and this is our n equals 2, n equals 3, etc. And this is where we have ionisation. And these arrows represent the types of opacity that we might have in a star. So now, just before I move on, just want to ask the question, and this will really reflect if you've seen these sorts of diagrams before. In this schematic, the arrows represent changes of energy for what? That's okay, yep. All right, so it is electrons. So as the electrons are moving, because remember we're talking about an atom, so we're not worrying about the nucleus here. So as the electrons are moving between energy shells, if they absorb energy, they will move into a higher energy state, and likewise if they absorb energy, they move into a higher electron state, but then they can lose energy, then they can emit photons. All right, so let's look at now what some of these different arrows represent. So let's just focus on this particular arrow motion. So we're going from the n equals 2 above beyond the ionisation state. So what does this represent? What does the red arrow represent in particular? Yep, okay. So mostly yellows, which is good. So that's bound free. Because again, you're moving from an electron. If we have an electron here that's bound and it absorbs energy, it will release a photon. So then we have, likewise, if you have this particular configuration, so again you have an atom, it has a photon that it interacts with, and it's a bound transition. That is correct. What about this one? Well, that's hopefully now that one's obvious. It's a free-free transition again. So this is just interacting with electron. Yep. What about this one? I didn't actually draw that, and I thought that anyway. I'm sure I thought that was an interesting little diagram. Yeah, I think by the process of deduction, it's probably going to be the last one, isn't it? Yeah, exactly. All right. So deep in stellar interiors, the atoms are really highly, and we can generally assume they're fully ionized. And the photons in the central regions of stars are very energetic. So we're talking X-rays and gamma rays, even in the centre of our sun. So what are the expected sources of opacity under these conditions? Well, there might be more than one. So in fact, there are actually two valid answers here. Yep. Okay. Yep. I can see mostly one or two colours, which is good. So it is free and scattering, because again, if you have a region that's highly ionised, you've got a lot of electrons. So the electrons have been ionised from their atoms. So you can have free processes where electrons will absorb photons. And likewise, you can have many scattering processes as well. And these are the two radiative sources that dominate deep in stellar interiors. Even as I said, in our sun. Even in our sun, the energy that would be generated would be in the gamma region of the spectrum. But of course, by the time it scatters its way out, it moves its way out, it is released in the green part of the spectrum-ish. Okay. So this comes back to the next part, stellar colours and spectra. So we've talked a little bit about opacity. So now we're going to relate this back to what we see when we see stars. So some of this might be, I actually quite like this lecture because I think it is getting back into more what we see when we see stars, and it's getting into relating maybe the observations with the theory in a bit more detail. Some of it's even revision from first year or second year for those who have done that. Okay, so this is a globular cluster M15. It's a particularly old system in the halo of our Milky Way galaxy. This is a poor resolution image from the mid-90s of the central regions of this cluster. I found an updated region from Hubble Space Telescope. Isn't that amazing? So when we look at this cluster, we know this is an old system. So globular clusters tend to be on the order of, say, 10 to the 5 solar masses. They're old. They're all about 10 gigayears old, especially what we call the metal poor clusters in the halo. M15 is a particularly interesting cluster. If you remember, we discussed ion abundance, and we had this square bracket notation. M15 is about minus 2 point something, 2.2. I can't remember off the top of my head, but something like that. So if we convert this, so this is going to be Z solar times 10 to the minus 2.2. So it has a very low ion abundance in general. And the thing is about we think about these clusters is we think they formed all out of the same gas cloud. So all the stars, within some precision, have the same ion abundance. This cluster has other weird anomalies that I don't want to go into here, but this is an example of the sorts that it's all old, but you notice that we still see variations in colour across this cluster. And so the idea is that we want to understand why this is and what's causing this. Okay, colour and black body. Of course, we know that if you have a hot object, you put it through a prism, that you'll see a continuous spectrum. In reality, of course, we see absorption lines. Sometimes we see emission lines, but we'll get onto that in a minute. So this is really revision from first year. Black body radiation, if you increase the temperature, the total energy radiated increases, and the peak wavelength that's emitted will shift towards the blue. So if you have a very hot object, the total flux emitted is higher, and the wavelength that will be emitted, the peak wavelength will be shorter. That's why hot things appear blue or white, and cool things appear to glow red. And they also release much less energy. Actually saw a very interesting plot like this that included a brown dwarf on it, which we don't get into brown dwarfs here because they're not actually stars, but brown dwarfs here, if you want to put it, it's over here somewhere, and it would have this little blip down here. So brown dwarfs, because they're so cool, I think their temperature's like 1,000 degrees Kelvin, but they emit such little flux, again, because it's because of this relationship. Okay, so this is something that we all know. again, red stars emit most of their light in the red. And there are many red cool stars out there. And then we have hot blue stars, of course, that emit most of their light in the blue or the blue-white. Now, when we talk, so this is again, we have a hot body and we're looking at it through a prism, we get a continuous spectrum. But of course, we know in reality there are absorption lines. And each element in the periodic table has its own unique set of absorption lines. And in fact, the first spectral classification wasn't even using this beautiful table of elements, but it really mostly was based on hydrogen lines in spectra. So how does this work? We have absorption and emission lines. Again, this is our hot object. If you see it through prism, you see a continuous spectrum. But of course, most stars in reality have an atmosphere. And so when the light from the hot central regions moves through the atmosphere, you get absorption in that cooler atmospheric region. And that's why we see absorption lines in the sun spectrum. Okay? That's where the absorption lines come from. If, for example, you have a hot gas, a hot diffuse gas, so this might be you have a hot region in the Milky Way galaxy, and it is hot enough that that it's emitting light. In general, in this case, you would see emission line spectra from that hot gas, hot diffuse gas. So this is trying to give you some of the physical reasons for the differences in a very qualitative way. Yeah, someone put a stars around here. Yes. Okay. But each of these lines has a unique spectra. And actually trying to find, if we go back here, if we're trying to find lines for some of these elements, we actually have to move into different regions of the spectra. So for example, finding lines of lead in particular, where lead is here. Lead's a very interesting element for many reasons, but we have to, if we want to observe absorption lines of lead, we have to move really into the blue part of the spectra. Some of these lines, like germanium, to pick a strange element, you have to go even into the UV as well. So, but in general, when we classify stars, we really only use hydrogen, mostly hydrogen and helium. Okay, that's just a summary of that. Okay, so these are the main spectral classifications, O, B, A, F, G, K, M. There are all sorts of monikers to learn this. I generally think that they're all a bit outdated. Choose one if you want to try and memorise them. But the main thing is that hot stars are up here, types O and B, and as you move down through this sequence, you move to cooler temperatures, cooler surface temperatures. Remember, he was specifically talking about the outer layers of the star, so not the interior temperatures. So you'll notice that there are different absorption lines, that the peak of the absorption lines are actually around A and F, and that is because this is where, these are the hydrogen Balmer lines, and they're most easily seen in these types of stars. And there are physics reasons for this, of course, because here, those hydrogen lines, we need to have stars can't be complete, so stars can't be so hot that they're completely ionized, or you don't see any absorption. That's why we see very few absorption lines up in the Balmer region up here. And down here, it's almost the opposite. These stars are too cool, so they're not doing any of that absorbing of those hydrogen Balmer lines anymore. And in fact, most of these lines now are actually dominated by molecules. So these stars are cool enough that some molecules have formed in the outer atmospheres, like cyanogen, CN, or sometimes even water will form. And so we're seeing absorption lines from molecules instead of atomic transitions. Okay, so these dark lines, they represent absorption lines of particular elements, mostly hydrogen, but also molecular lines as well in the cooler stars. And so very early on, we actually didn't know. So you notice that it is a strange sequence in terms of the letters, and that's because when they first started classifying stars, they based it on these lines. They didn't understand the stars were even made of hydrogen at that time, and they just said, okay, we see that A-type stars have the strongest lines. So let's start, so they went O, A, B, and there was even then they had a few other classes which got absorbed into others. Then they went F and G, and it was only later that they related these sequences with colour and temperature. And then they related that those colours actually represent temperatures. That came later, and that's why the sequence is a little bit off. The interesting story actually also that they didn't know it was hydrogen, and the first person who said it's hydrogen, her supervisor said, don't publish that, that's wrong, that's crap. Stars aren't made of hydrogen, they must be made of the same things as the Earth, but later then he published that stars are made of hydrogen. So anyway, science isn't always a fair game. Okay, so there's not much light here, and that's because these stars are so hot that we aren't, well actually there is, well they actually don't emit much light in the red. You also notice that there's not much light down there because our red stars don't emit much light in the blue. Okay, and this is increasing temperature, which I think is actually obvious on the right-hand side. Okay, so these are our spectral classifications. We've also now, this is very hard to read. It should be hopefully read more easily seen in the PDF version. But this is, we have nanometer, so from 400 up to 650 along here. So these lines here, these are actually ionized calcium lines. We have a strong sodium line that we see here, etc. So we can identify various lines according to various elements. Okay, but all right, so this is just a summary. So we have O, B, A, F, G, K, M. I've actually added those 3 LTY. These are spectral classifications that were added later on. These are for brown dwarfs. There are also an alternative sequence. So we have O, B, A, F, G, K, M. And then there are the cooler sequences. M actually splits into a few. So there's an alternative sequence with which have the same temperatures as the R, N, and S. These ones I'm not sure you really need to know, but at least being aware of this main sequence is the thing that we would be expecting. So there are various mnemonics you can use if you want to. Try and learn them. It's up to you whether you, some of them, as I said, are a bit old-fashioned. So each of these sequences are divided into 10 subclasses. So for example, the B subclass will be B0, B1, B2, etc., where this B0 is the hottest and B up to B9 is the coolest. Later on, of course, we have linked these subclasses into not just temperatures, but also stellar masses when we talk about main sequence stars, but we'll get onto that. So our sun is classified as a G2 star. And what does that mean? So when people started making diagrams of these things, first of all, this is also another historical artifact, I guess, for astronomy, is that they started plotting them. So they noticed, okay, so let's plot O, B, A, F, G, K, M like this. And it was only later that got turned into temperatures, and then they realised they're plotting their temperatures around the wrong way. But we've retained this historical artifact. So when we look at what's called a Hertzsprung-Russell diagram, we plot it that the temperature decreases in this direction, but at least the luminosity, so we relate, this is something we'll learn about later, but usually this is measured through the absolute magnitude of the star, and that we relate to the bolometric luminosity, and that at least goes in the right direction, where we have the coolest, so we have, the least bright stars down here, such as white dwarfs and M dwarfs, and the brightest supergiants and other sorts of stars up there, up in the top that I can't reach. So this shows a Hertzsprung-Russell diagram for stars close to our sun, for example. And we say that our star, that all the stars along here, and again, you probably know, most of you probably know this, that these are our main sequence stars. And we see most of the stars in the night sky on the main sequence. We see some giants, we see some supergiants, and the difference is just brightness. I got really confused at some point why they're supergiants and giants, and it's an observational thing, basically, and it really just comes down to how bright they are. It's a little, the lines that divide them is quite blurry. Then we have, so these are our main sequence band, where these are the dimmest, coolest stars, and these are our hottest, brightest stars, our giants and our supergiants. Then we have our white dwarfs here. There's not many white dwarfs close to us. Sirius B is around the star Sirius, and Procyon B. There's now, of course, we know of many more of them. So So in the old lectures, this is the diagram that was included. This is a bit hard to read because, again, this projector in this room's not very dark. So again, this is now colour instead of spectral type, but colour we relate to spectral type and temperature. And this is, again, luminosity. So this shows stars from what's called the Hipparcos catalogue. Hipparcos was a satellite that was launched around the 90s maybe, don't exactly remember when, maybe even the 80s. And it was measuring the distances and the positions of stars. So this was for about 22,000 stars. So yeah, okay, it launched in the late 80s. Since then, we've had Gaia, and I'm going to show you a separate diagram. So before I show you a more modern diagram, so this is our main sequence band. As I said, there are subgiants, supergiants, etc. up there, and white dwarfs. We actually have separate luminosity classes. So along with having our spectral types, A, B, O, B, F, etc., there are also luminosity types. So these relate the position of the star in the main sequence to some thing like a dwarf or a giant, etc. We have since related these to stellar evolutionary, where they are in terms of their stellar evolution. So dwarfs generally mean main sequence stars. If they're giants, they might be a G2 giant, like that. And that means it's a giant branch star, so it's evolved off the main sequence. So we have if you read, especially older textbooks or some papers, will still refer to these luminosity classifications. I try and not stick to them, but okay. Just to show you a more modern HR diagram, this is from the Gaia satellite. This was launched in 2013. This here, now we're seeing 4 million stars on the HR diagram. So again, this is colour. This has been cut off. Apologise. This is Gaia absolute magnitude, which is related to the absolute brightness or the luminosity of the star. And here, just to show you, we had 2 white dwarfs in our stars closest to the sun. We now have hundreds of thousands of white dwarfs as well. This is a pretty amazing diagram, I think. So that's what I mean. I think I mentioned one of the earlier lectures that you guys are living in a different era in terms of astronomy data, and that's what I mean by this. This is just a small subset of what Gaia is going to deliver us. It's eventually going to have about more than 1% of all the stars mapped in our galaxy, which is amazing. Anyway, so just shows you now we have this beautiful main sequence band, giant branch, etc. Again, we have our luminosity classes and white dwarfs. Just to put them side by side, I've tried to put them on similar scales here. So you can see now there's a couple of, you can't really see this very well, and I can barely see it myself, but there are some white dwarfs here compared to the many, many, many white dwarfs we can see in the more modern diagrams. Okay, so which stars are the most common? I think, hopefully, especially looking at the Gaia diagram in particular, it's quite clear that the most common stars are the ones we see down here. And these are M dwarfs. By far, they are the most common stars, by far. So if we were to make, for example, a diagram like something like this, where we can see the numbers of stars on a XYZ plane, where here this is absolute magnitude, this is spectral class, and this is the numbers of stars here, our M dwarfs by far dominate. And we will learn, don't know if we will get into, if you looked at star form, how stars form and things called an initial mass function, we have since related this because we know that most of the stars that are born tend to be low mass, at least today. So that's why we see mostly M dwarf stars. So when I say our sun is an average star, that's actually incorrect. Our sun is slightly more massive than most of the stars in our galaxy. Okay. Now, let's go back to opacity. Which of the processes produce the lines visible in stellar spectra? Do you think? So remember, we're talking about the atmospheric regions of the star now. So we're not talking about the hot interior, we're talking about the outer layers. That's where the photons, because we have a hot region, the photons move through the atmosphere, and it's in that atmosphere where those lines are produced. So what's dominating? What are the opacity sources that dominate in that region? Think about would the atoms be ionized? Probably not. It probably would depend on the surface temperature, but probably not. You can see mostly some colours, and it is mostly bound because mostly they're not ionized. So in most cases, the atoms aren't ionized. So the electrons, so again, the photons are it's again an absorption process. So you have an atom, it has its electrons, it's absorbing a photon, and then it just absorbs a photon. And this is why we see, and that's why we see those lines in the stellar spectra. And indeed, people who, we don't talk about radiative transfer at all, so you'll be thankful to know this is really probably a fourth year topic and beyond. But if people are trying to measure, let's say you see all those beautiful absorption lines in stellar spectra, and you want to try and work out what a star is made of. And and again, they tried doing this in the 1920s and they got it wrong because, it was even earlier. I think, first of all, it started earlier than that. But it was really in the 1920s where they related those absorption lines to the Saha equation, and they said, okay, and radiative transfer, and then they said, okay, the stars are actually mostly made of hydrogen. But what else are they made of beside hydrogen? And so in order to learn this, we use those absorption lines to try and determine what the atmosphere of the star is made of. And then we try and make an assumption that if the atmosphere is made of if it's some small percentage of oxygen, then the whole star is that same percentage of oxygen. So this is what we say what the star's made of. So how do we do this? Well, we take an absorption line. So this is a sodium absorption line in a real stellar spectra, or this is an aluminium absorption line in a real stellar spectra. This is iron, as an example. And then what people do is they try and, again, they make a model, a detailed model of that atmosphere. So they don't worry about the rest of the star now, just the atmospheric layers. And they have a radiative transfer model of those layers, and they have to treat opacity in those layers and how the photons are moving through. They make generally lots of assumptions about how the photon moves through those layers, and then they say, okay, given all of this, what does the absorption lines look like in that star of that temperature, of that type, of that evolutionary type, main sequence, giant, etc. Because a giant star has a very different atmospheric model, it has a very different type of atmosphere, much less dense, much cooler than a star like our sun, which is more like 6,000 degrees, and it's not such a diffuse atmosphere. So, and generally they will adjust some of these parameters, such as the temperature a little bit or the surface gravity of the star, until they will match. So this is the model there, the solid line, and then they'll try and match until that matches those points there. And they say this is the sodium content of the star. So the sodium surface abundance is this, and that's how they try and do it. And this is how we get, for example, the solar photospheric abundances. And it's and then this is why we can get it for some elements like sodium, but it's hard to get it for some elements. Impossible, for example. If you can imagine, for example, the noble gases, we can't measure absorption lines there aren't absorption lines for the noble gases. So we don't measure, for example, neon, argon, krypton, all of those elements, we don't measure those in stellar spectra. We can measure them in diffuse regions though, because they emit emission lines, but we can't see them in stellar spectra. Okay, so this is a summary about bound. I'm not going to read it here. I'll upload this and you guys can have a read of this. This is really for your reading for later. But I think the main point is that, and there's also bound free, free, and scattering. The main point is that we just to have a bit of a so my expectation is you'll have a qualitative understanding of what these 4 opacity sources are. Okay. So what do we do in real stars? Well, here now we have to treat the opacity as a function of the density. So this is log density in grams per cubic centimetre. This is the temperature. This is log temperature in kelvins. And this is a diagram that shows what dominates the opacity in stars. So for example, in very high density regions that are fairly low temperature, conduction will be dominant. And this is, for example, such as a white dwarf interior. Here, for example, in lower density, lower temperature, we'll have molecules, we'll even have dust grains that can scatter and absorb light. We have also bound free and bound. So again, it does certainly depend on the temperature. As you move towards hotter, for example, you end up going to bound free, and then you end up with scattering as well, and electron scattering. So when we look at opacity sources, generally what I would take are tables. So I would download tables for a star of a given composition, and I would say, okay, and then I would break up my star into different mass shells. So where this is the centre to the surface, and I have to find the opacity at each mass shell depending on the temperature, the density, and I have to do that as I'm evolving a model of a star every time for each of my mass shells, and generally I might have 1,000 of them or 2,000, I would be having to find the opacity at a given temperature and density at each of those mass shells in order to make a model of a star. So I would need to have opacity tables that include all of this so I can do some good interpolation, not extrapolation. That's where things can go horribly wrong. So our opacity tables might look something like this. Generally, they're never complete, and as well, they're never regular grids either. Sometimes they're missing certain regions. So this is the radiative opacity as a function of density and temperature for a given composition. It's very high. It's a very high metallicity here. So this range of values is applicable for the outer regions of stars. Although the outer regions of stars very, very rarely have those sorts of metallicities. So for example, that's the opacity here. That is meant to be a kappa, so that's log opacity, and this is log temperature. So this is the coolest region, the hottest region. This is moving out to higher. So this is moving inward into higher densities. So you can see, for example, according to this diagram, that the opacity is actually quite low in our cool temperature regions of the star, our radiative opacity. But this is just radiative opacity. This actually doesn't include molecules. If you were to do it properly, you would need to include the contribution of molecules and dust grains, and their contribution increases in this particular region of the parameter space. But again, generally there are tables online that I would download, and I'll have to supplement my radiative opacities for my molecular or dust opacities. Okay. Final thing in this particular lecture, we're just going to look at the Eddington luminosity. So this is the maximum luminosity that a star can have. So photons carry momentum, we've learnt this. Photons also exert pressure, we've also learnt this. And so that means there can be a maximum photon flux for hydrostatic equilibrium. So that is again for the star to stay balanced in hydrostatic equilibrium. So let's start with our hydrostatic equilibrium equation. So from before, this is dPdr equals minus rho gm over r squared. So let's start here. So this is a fairly nice, simple, easy calculation. I won't do it on the board unless, I don't think we'll need to, although I'm not sure I can reach all of that. Okay, so let's assume our P now is just radiative pressure. So we're assuming that we have no gas pressure. All of our pressure is coming from radiation. Now, we have dPdr equals, so all I've done here is said now this, so now this is the P, where this P is P of R. Okay, so this is our radiation pressure. So let's differentiate this. So we have dPdr over dr, 4 over 3a t to the third dTdr. Now, we also have our temperature equation from before. So we can use the diffusion equation for dTdr and just rearrange for dPdr over dr, and we end up with this expression here. So now we can equate the two. So remember, this is our hydrostatic support. This is our this is our expression from here, and we can rearrange for the luminosity, and we get this term here. So this is 4 pi times the speed of light, gm over k. Kappa. I think that should be a kappa. Should be a lower kappa. Yep.
This is like a limit, like a maximum luminosity.
It's a maximum luminosity. So what we're trying to find is if, for example, radiation pressure was providing all of the pressure, so we have no gas pressure, is there a maximum luminosity for a star to have to stay in hydrostatic equilibrium?
So it must have and there's probably some gas pressure as well. So
in reality, in reality there would be. But the thing is, so in this case, so let's say if we have a luminosity that's higher than this, the star, a star could have a luminosity that's higher, but it would not be in hydrostatic equilibrium anymore. So it can't stay balanced in hydrostatic equilibrium. So it would do something else, like explode or have some other experience. So that's what this luminosity represents.
What's the fraction of gas pressure or radiation pressure again in the star? Is it mostly radiation pressure?
It depends on the temperature, a lot. So the temperature, so for a star like our sun is something like 100 million degrees Kelvin. If the temperature in the centre was about 100 million degrees Kelvin, then the pressure would be dominated by the radiation pressure. But a star like our sun, it's probably something like 99% dominated by gas pressure at 15 million degrees. So in reality, there's always a contribution from both. But in some stars, especially stars like our sun, the contribution from radiation is so tiny to be basically negligible. Yep. But this is the case where, so this is the extreme case. It's like an idealized case. And this is also the case that breaks hydrostatic equilibrium. That's why it's an interesting case. And you'll often hear actually people talk about, this is actually called the Eddington luminosity. So it is a kappa on the bottom. And this is often referred to in the case, people talk about more in terms of accretion rates. So for example, if you have a black hole that's accreting and matter from an accretion disk, and they say that it will release energy as the matter is being accreted, and that they might say that luminosity is higher than that the black hole could only grow if the luminosity is higher than the Eddington luminosity. You might hear these terms. You might even see those, especially if you're reading press releases about how black holes grow. You might read these terms. But this luminosity is that when they talk about the Eddington luminosity, this is what they mean. So it's a luminosity that's higher than for that object to stay in hydrostatic equilibrium. Okay. So our luminosity depends on kappa. Okay. Or I should change that. That's okay. I should actually write that out. So this means if the luminosity exceeds this value, then hydrostatic equilibrium is basically impossible, and this is known as the Eddington luminosity. We can rewrite this actually in terms of many of those 4 pi, speed of light, g. These are all constants. So we can rewrite this, make some approximation for the opacity k, and we can write this to be approximately equal to 40,000 times the mass times the solar luminosity. So this is another alternative expression for the Eddington luminosity. Okay, so from the diffusion equation, so we can also, if you remember when we were looking at our main sequence stars, so we had this sequence on the HR diagram that looks something like this, where this is T decreasing, now put increasing in that direction, L increasing. So we can actually see, and usually there's an expression where we have something like L is proportional to m to the third. So we can relate the luminosity of these stars to their masses. And we can get this expression just from these equations. So starting from the diffusion equation, again, let's just take order of magnitude. So T over R, we're not worrying about, again, this is really just really simple order of magnitude, is rho times the luminosity divided by R squared over T to the third. So we're dropping all of the constants, not worrying about the negative. Okay? So approximately equal to, very approximately equal to. Rearranging. So, and then we're putting in for rho. So rho, remember, this is mass divided by volume. So this is our mass divided by volume here. It's approximately equal to m times L, R fifth to the T thirds. That means that L is approximately equal to this. Just rearranging. Or R4 T fourth to the m. Now we can take this further from the equation of state, where P equals rho RT over mu. That means pressure is, again, remember, order of magnitude, m R cubed times T, where let's not worry about the R over mu. From hydrostatic equilibrium, we get to P over R. I think you can see where I'm going to go with this. We get P over R. And again, for rho, m over R cubed times m over R squared. So P is m squared over R4. Equating our expressions for P, we have mt over R cubed, approximately equal to m squared over R4. So T is m over R. Now we can substitute that into the previous expression. If you remember, we had this from before, L. So let's just, and we get, so these are our two expressions, and we end up with L to the power of m cubed. And this is meant to, let me just explain why essentially stars, this allowed us to relate, when we didn't have a good understanding of what the main sequence lines represent, from doing this is basic homology relationships, we could relate the luminosities of stars to their initial masses, at least in an approximate sense. Again, it's very order of magnitude. It gives us just an order of magnitude approximation of the masses of stars. Since then, and especially now we're in the era of Gaia, we have precise distances to stars, we have precise positions of stars. So now we can actually estimate their masses much more precisely without worrying about all of this homology stuff. But when we didn't know that, because distances in astronomy are particularly difficult, and they have been historically very, very difficult, this was the way that we would get an estimate of stellar masses. Especially for stars, single stars in the field that aren't, and I mean in, for example, the galactic field in the thin disk, where that aren't in binaries. Because if they're in a binary, we can estimate their masses quite precisely. Okay, almost done. There are limits on radiation. We just saw one, the Eddington limit, but there's also buoyancy. And so we need to worry about convection. And this is the Schwarzschild criterion. I know, isn't it? It's awful. I left it almost because it is so awful. Okay, so that ends this lecture. So this was a bit more qualitative, just trying to understand opacity and looking at stellar spectral classes, etc. In the next lecture, we're going to look at convection, which will be fun, also fairly qualitative.